So I'm going to basically use the same scan that we had there. And this is basically what it looks like. And then I wanted to basically go through the exact same process that we've gone through so far, but this time the ICP. And I wanted to show you that if we do it 0.1, what would happen there in terms of our distance threshold. And then the STL is basically the sound or the foundation or whatever. The foundation is important because if you do it with the sample mesh, it doesn't really change anything. But if you do it only with foundation, because now a significant portion of it would be covered by the ones on the top and the bottom, then it's going to have some problems there, right? And then if you basically go through this, you're going to understand that there's a significant impact and a considerable error that is going to be produced here. And this is basically a good transition into why the curvature-based methods would provide some minimum benefits. So then when you wait for it, you're going to see that the RMSE is 0.3. Then the error actually is increasing. That means that it's not converging. Essentially, it used to be in a convergent state and it's now diverging for it to a worse solution. And if you take a look at how the plot is going to look, basically looks something like this. Where it's almost completely sideways because we're looking at this foundation, right? And if it's only this foundation and you increase the distance, then it's going to take quite a bit of the points on the surrounding from the column on the top. Now, what this ends up happening is that it creates a situation where it must register it in a different way. If it doesn't register it in a different way, then it's not going to work. And this is what the major problem here is that we really, the distance threshold is so significant in our computations that really we must either know it by heart beforehand, meaning that we have to perform this multiple times with different distance thresholds, which for larger sites would be quite complicated and challenging. Or we basically would have to create a situation where we use other types of information for this. And if we use other types of information like curvature, like whether this set of points actually do follow a planar surface or not, all these types of things. If you take a look at the error there, just by changing this, this is now converging. It's not diverging, okay? It's not getting large, it's actually getting small because that's what we want. We want our RMSE to get smaller. That means that we want to get closer to the solution, not farther than the solution. And that's why it gets tilted. Okay, and then we go and take a look at that. And when you see that, you're going to see that there's, you know, between the actual original and what we see here, which I've colored it in magenta, it's quite similar and it actually gives you a better result. The red, however, is quite significantly different. And that is exactly what I wanted to make sure that we focus on, that it's very, very important for us to make sure that that distance threshold is properly set. Now, one way to solve it not going up is to basically prevent it from going up, basically saying if our error in our I+1 is larger than our error in I plus or I, then we basically say no, you know, we're not going to go forward. The problem is that that means that you might have a local convergence, but you might converge later on to a global convergence. But you can do that as well, just to make sure that at least it doesn't completely screw up your solution, meaning that at least a solution at a previous iteration is not completely worse than the final solution that you're going to get. So that this part will give that benefit, but overall it wouldn't.